I hope you're hearing me. Hi, everybody. And thank you very much for this opportunity to introduce myself and share my research. My name is Emre Tepe, and I'm an assistant professor in the Department of Urban and Regional Planning. My main expertise is on spatial econometrics and urban modeling, and my main academic interest is spatial temporal modeling of urban systems. With this short presentation, I would like to introduce the latest advancement in spatial temporal modeling of land development dynamics. Modeling land use change is a fundamental task in urban and regional planning because such models provide vital information for urban planners and policymakers. These models will tell us how human activities form urban space and structures. For example, using such models, we can predict if environmental sensitive areas are under pressure of new land developments. As similar to many other good things, modeling land use change are not an easy task because such models requires incorporating so many complex dynamics. Many researchers from various fields have been working on multiple different approaches to deal with the complexity. And today I would like to talk about the most prominent approach that are likely to make significant impacts in the field. Parallel to the increasing availability of spatial and temporal data, dependencies exist in these dimensions can be incorporated in land use change models. However, this is not an easy task as well. Existing methods to model spatial temporal dynamics in land use change models are not suitable to use for large urban areas. Existing methods can only work up to 2,000 spatial units. When you consider an average city generally has more than 50,000 parcel, we can also see why these methods are not feasible. In 2016, I introduced a simulation-based autologistic regression model. This alternative method is an effective approach when we have a large data set because this method does not require to compute inverse of a large matrix. Computation of a matrix inverse is a costly task. It may not sound a big deal, but I can tell you most data scientists will do almost everything to avoid computing inverse of a large matrix. Even though this method is feasible for large data set, unfortunately one downside of it, it won't guarantee convergence every time. So then another alternative approach is being considered in the field, machine learning and artificial intelligence. These methods are generally considered as a suitable for large data sets. And recently, spatial and temporal models have been introduced using these methods. These methods will be suitable to develop a large-scale land use change models. Especially use of these nonlinear models available in ML and AI domains will allow us to control complex nonlinear spatial relationships that were not possible before. The only downside of using these methods, they won't provide the inference of estimated parameters as we have in inferential or Bayesian statistics. Finally, land use changes are mainly considered as a category change. However, as land uses are changing, shapes of those lands are also changing. Hybrid land use change models are being also considered for estimating both potential land use categories and its shapes. Algorithms to find optimal land development require solving a complex optimization problem. Conventional methods may not be suitable even with small areas. However, efficient machine learning algorithms like genetic algorithms could be a way to solve such complex optimization problems. In my recent research, using these new methodologies, I am hoping to develop a realistic land use change model that can explain many dynamics that are happening in the real life. And I would like to thank you again for this opportunity and for your time and attention.